All right, Advent of Code, day 14. Here we go. Docking data. As your ferry approaches the seaport, Captain asks for your help. Captain asks that this runs. Computer that runs this isn't compatible with the docking program. Docking parameters aren't being correctly initialized. You discover that the Seaport computer system uses a strange bitmask system with its initialization program. Although you don't have the correct decoder chip in hand, you can emulate it in software. Initialization program, your input can either update the bitmask or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. Values and memory addresses are both 36-bit unsigned integers. For example, ignoring bitmask for a moment, a line like memory 8 equals 11 would write the value 11 to memory address 8. Okay. The bitmask is always given as a string of 36 bits. Whoa. This is crazy. Okay. Written with the most significant bit representing 2 to the 35th on the left, least significant bit 2 to the 0 on the right. Current bitmask is applied to values immediately before they are written to memory. A 0, 1 overwrites. Okay. Specifying a mask. The mask it specifies will overwrite 2 bits in mask it specifies will overwrite 2 bits in every written value. The 2's bit is overwritten with the 0, and the 64's bit is overwritten with 1. Oh, I see. The program then attempts to write the value 11 to memory address 8 by expanding everything out. Okay. Got it. Stirs. Okay. And when you write to memory, it overwrites everything, right? Okay, got it. Mem equals hash z hash stirs dot each do stir cur mask equals that, I guess. And then okay, if stir start with mask else ms equals stir dot split 2 ms dot cars dot each do each with index do chi cur mask for 7 2 1 0. Oh. Okay. Whatever. Okay, so cur mask equals this. Okay, so how do bitmasks work? All right. So it's 2 to the 6th, 2 to the 35th. 2 pows equal dot times map n 2 to the uh, 36 minus 35 minus n. If mask equals, or if ch equals 0, to cur mask 2 pows I equals 0, else if n equals stir.scan f mem. Okay. Equals stir 400.2i val equals stir dot split 2.2i. And then 1, 4. Okay. So actual val equals 2 to the 36 minus 1. All bits. So okay. Mask equals 0. Mask val mask or equals 0. So if it's a 0, let's see. I want to AND it with 1s where the x's are. Val equals val and mask or mask or. That's what I want. Okay, and so if else if ch equals x, I want to do mask equals 135 minus I. Yeah, because when I is 35, the last one, this will push it 1 over and 1. Cool. Otherwise, mask or plus equals oh, if it's a 0, nothing. And if it's a 1, yeah, mask equals pseudo I'm in the middle of something, mask or equals 0. Okay. And then what is it? Mem dest equals val. Puts mask val. Puts val became mask val. $11 became $73. 101 stayed 101. 0 became 64. P equals 1. Mem dot values dot each n p times equals n puts p. Okay, I think, oh, the sum. Boom. Okay, that's 489. Oh my God, this is impossible. People are so good. For some reason, Seaport's computer system still can't communicate. It must be using version 2. In version 2, it doesn't modify the values being written at all. It acts as a memory address decoder. Immediately before a value is written to memory, each bit in the bit mask modifies the corresponding bit of the destination address in the following way. If the bit mask is 0, the corresponding memory address bit is unchanged. If it's 1, it's overwritten with 1. Okay. And if it's X, it's floating. A floating bit is not connected to anything, and instead fluctuates unpredictably. In practice, this means the floating bits will take on all possible values, potentially causing many memory addresses to be written at once. Okay. Mem equals z hash dot new. Oh. Okay, it doesn't modify the values. I see. So it modifies the destination. Oh my goodness. Okay. So let's have Z mask, O mask, and X mask. O mask. Or no, that's Z mask, O mask, X mask. And then Okay, so let's first handle these two. Dest. If the bitmask is a 0, it's unchanged. Okay, so I ignore zmask. If it's a 1, or equals O mask, and then okay. One, two, three, dot combination, dot permutation, no, combination. That's not what I want. Okay. And then, so I first want to remove the things dest and equals all bits minus x mask. And then on bits equals equals 2 pows dot select do TP what mask is it? X mask. X mask. Or and TP greater than 0. Puts on bits dot inspect. EX1 75. O mask. Oh. Wow, that's a lot of, oh, okay, but, okay, not a lot of values. 0, 2 to the on bits minus 1 dot each do n mask floating bits equals 0 on bits count dot times do I if I and that's greater than 0, floating bits plus equal on bits I, mem o dest plus floating bits equals val. Puts writing to dest plus floating bits val. Each. Oh. Writing 11 to 64. Puts how am I infinite looping? Put on bits dot inspect break. Man, I'm not doing well on this one. Oh, okay. Example 2. So puts on bits dot inspect oh, that's n. Okay, I'm like kind of close. So 26, 27. 32 and 1. Why isn't the 1 working? Puts n puts to I puts and n is 2. Oh, do I need a -1 here? So, shoot. Oh. $26. Oh, it worked. 16, 17, 18, 19, 24. Okay. So now I just need to get rid of that, and then there we go. Yay, I did it. Wow, I'm not good at bit stuff. Not good at all. Okay, but I did it. I did it. Part 1. There we go. Oh man, I totally forgot to stop my timer. Whatever. All right, let's go back to this problem. All right, so what is the story part of this? Man, when I started reading this, I was like slightly distracted, and the words that I said did not match this at all. Let's make sure you can see everything. All right, day 14, docking data. As your ferry approaches the seaport, the captain asks for your help again. The computer system that runs this port isn't compatible with the docking program on the ferry, so the docking parameters aren't being correctly initialized in the docking program's memory. After brief inspection, you discover that the seaport's computer system uses a strange bitmasks system in its initialization program. Although you don't have the correct decoder chip handy, you can emulate it in software. The initialization program, your input, looks like this, can either update the bitmask or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. For example, ignoring bitmasks for a moment, a line like mem8 equals 11 would write the value 11 to memory address 8. The bitmask is always given as a string of 36 bits. So if we look at our input, we're writing to like very large memory addresses. I'm going to end up using a hash, a z hash, which is a util I wrote that just initialized everything to 0. The bitmask is always given as a string of 36 bits, written with the most significant bit representing 2 to the 35 on the left and the least significant bit 2 to the 0 on the right. The current bitmask is applied to values immediately before they are written to memory. A 0 or 1 overwrites the corresponding bit in the value, while an X leaves the bit in the value unchanged. How we can interpret that is we want to we have our value, and we need to AND our value with all the X's, and then OR it with setting all the X's to 0, and then just the remaining things. So you specify a mask, and then it writes some stuff, and then the mask can be updated. And then at the end, you need to sum the value of all values left in memory after the initialization program completes. Everything is initialized to 0. The sum of them. So what we do is, we have a mask, which is going to be the X's, and a mask OR, which is what we need to OR stuff with. So if the string starts with mask, we need to update the mask. So we just initialize them to 0. We get all the bits, or all the characters. Then we loop all through the characters with an index. If it's a 0, that technically updates the mask OR, but the mask OR is already set to 0 everywhere, so we don't do anything there. If it's a 1, then we need to update the mask OR by shifting over 1, basically 35 minus I times, because if we're looking at the last one, I will be 35, and we want to actually just update our mask OR with 1. So we add that value. But if it's an X, we OR it, and really this could also be plus. It doesn't matter, I think. Yeah. So we have our mask OR and our mask, and then when it's not a mask, we get our destination, which is this part, and the value that we want to write to. And to update our value, we take the value, mask it with the mask, and then OR it with the OR mask. And that's our new value. And then we just write that into memory. And then we just sum up. Mem.values.sum. Originally, I thought it was product, which is why I wrote it that way. Cool. Still gets us the same stuff. Yeah, so that's part 1. Then for part 2, what happened is instead of actually modifying the value, the bitmask actually modifies the memory address that we're writing to. And so if it's a 0, whoa, Mr. Person, 154 for part 1. Well done. How did I do? 489 and 470. Very tricky. Let's see how other people in my crew did. Dang. Zrankiewicz is just dominating me. How about the Google leaderboard? Oh, very poor. I'm not very good at bit stuff. So for part 2, if it's a 0, it's unchanged. If it's a 1, we overwrite it with a 1. And if it's an X, then that's floating. And the floating means it can take all possible values, and it will write to all of those memory addresses. So how I did this is I keep track of a Z mask, which is 0s, O, and X's. And actually, again, if it's a 0, there's really nothing to do there. I don't actually do anything with it. Nothing. Are my masks are just exactly the same thing again. Plus equals 1, 35i. Yeah. I like, man, Eric has a way of like describing something in a totally different way that ends up being the exact same thing. Sort of. So then the floating bits, basically we need to do these things. So we OR it with the 1 mask, and then we clear out all the X's. So we have all bits, which is 2 to the 36 minus 1. So I clear those out from destination. So those are all 0. Then I have powers of 2, and that line up with the bits. And I filter that list of powers of 2 to just be the ones that are just the powers of 2 that were selected in the X mask. And then I basically take the length of that. So there, let's say you have 4 bits that were X's. Then I iterate from 0 to 2 to the 4th times. And then for each value I, that gives me like a value where like all the smallest 4 bits are either on or off. And I use that to detect whether I add the power of 2 to this like floating bits thing, and then I write to destination plus the floating bits. Yeah, I did not want to go into recursion, but Ruby I think probably has a better way. Power set function. Yeah, so this is what I could have done. Ruby has combination, which is like dot combination 2 puts x dot inspect. So what you could do is basically like have a one loop over how many items you're selecting, and then have a second loop over all the combinations of that many items. So that would look like this. 0 to on bits dot count dot times do n on bits dot combination n do comb floating bits equals com dot sum mem dest plus floating bits equals that. Boom, same thing. This is pretty clean. I like this approach. Yeah, I think this is the cleanest way to do it, at least in Ruby. You could even do it with like your recursion. You could even like start with 1 as your base case, and then like the value that you pass in to the next thing, like multiply it by 2. It's like all of these problems, like both this and what was I already forget what yesterday's problem was. Oh yeah, these bus IDs. Like, oh, Mr. Person, I saw a solution on the subreddit. If you just replace all the X's in here with 1s, then it just works, I think. Actually, or it works for part 2. For part 1, you might need to filter them out. But that's like a much cleaner way of handling it. Anyway, ignore day 13. So this is the way I did it. Much cleaner power set implementation. An actual useful Vim trick. Man, I love O for switching to the ends of a highlighted segment. Like, I can't, and whenever I try to highlight stuff with like the system highlighting, it just immediately frustrates me that I can't do that. Anyway, yeah, so part 2, still can't communicate. They realize they did something wrong. And then, yeah, that's it. Okay, so you fixed the computer system on the docking ferry. Yeah, so that is Advent of Code, day 14.